I think it's time to start. So, any question from this time? We are now finally getting into our quantum algorithms, and but as we have seen from this time, we are studying the complexity of quantum algorithms in this funny way, where we study the quantum query complexity. So yeah, so quantum query, we study the quantum query complexity because the time complexity is very hard. So we study this funny query model where we think about the input, not putting the input to our algorithm is not really from the starting state of your circuit, but we have those weird black box in the middle. So we think these black boxes compute some kind of function. So for example, in Deutch-Jorza algorithm, it's a 1-bit Boolean function. And really we think about the truth table of these functions, small function f. The truth table of this small function f is like a big N big input string, and this big N input string is really the input of our algorithm, and we want to compute some function on this input. Okay, so we have a very easy example of Deutch-Jorza algorithm here. So here our function is 1-bit to 1-bit, so it's like a small n here, and so big N is 2 because because there are 2 possible input, and so this is input string. So the actual input to our problem is like a 2-bit string, and so there are 4 possibilities. So f0 is too loud. Okay. So f0 equal to let me adjust this a little bit. f0 equal to 0 or f0. Let me try. This is better. Okay, yeah. So it's so the truth table of this small function f has 4 possibilities. So f0 equal to 0 or 1, and f1 equal to 0 or 1, and so 0, 0, 0, 1, 1, 0, 1, 1. And we want to compute the function on this truth table. And the function we want to compute here is f0 plus f1. Okay. And well, it's a 1-bit output, so there are 2 possibilities, and we list it here. So it's either 0 when f0 equal to f1, and it's 1 when f0 not equal to f1. And it's pretty easy to see that classically, if you want to compute this f0 plus f1, then you need to put 2 queries. Basically, you need to learn f0, then learn f1. Then you add them together, you will find out this f0 plus f1. But we see that if we define this funny quantum query, where you can have the superposition on the input and output register, then actually we can apply this phase kickback technique and compute f0 plus f1 in just 1 query. Okay, and yeah, so this phase kickback technique is when you have a Boolean function, so the output is just 1 bit, and you put a minus sign on the one output bit, then you find out that you get a phase of this phase vector minus 1 to the f of x on your input register. Okay, phase kickback is really cool. And yeah, so actually only 1 bit of actually 1 application of quantum query give you this result of f0 plus f1, as this Deutch algorithm shows. Okay, so this is the first separation we have between quantum and the query. In more general, okay, so more generally quantum query is like this. So you have an arbitrary function, maybe 0, 1 to n to 0, 1, and then you think your query is a big N bit string. Although we will see in one example where sometimes the output is not 0, 1 bit, then your input is another bit string, so it's like this string. so this function value might be different. But anyway, it's like a really long string. Okay. When the output is 0, 1, then we think this is a 2 to n bit string because there are 2 to n possible function output value, and you want to list your whole truth table. And our query complexity is thinking how many of those bugs do you need to put in your algorithm. so your circuit, to actually solve this question on this truth table. Okay, and yeah. So anyway, back to the separation topic. So our Deutch-Jorza algorithm shows that we can compute f0 equal to f1 with just one quantum query, and it requires two classical queries. So we have the 2 versus 1 separation. And now the question is, can we get bigger separation between quantum and the classical query? And that'll give some evidence that quantum computer has speed up over classical algorithm. And yeah, so this is really important. I guess that's the most practical topic in quantum computation. That's whether quantum algorithm runs faster than classical algorithm. Okay? Yeah. So yeah, so this is the main focus of the study, and we'll see 3 algorithms today, and shows beta and beta separation between quantum query and the classical query. So any questions so far? No. Okay. Yeah, and yeah, so next question, well, is then from then you probably see that it's the generalization of the algorithm that's talked about. So it's Deutch-Jorza algorithm, and yeah, it's a generalization of Deutch-Jorza algorithm. And what does it do? Okay, so you will show exponential separation in some sense by extending the function to more input. Okay, so now the truth table is longer. That's why you can have more separation, right? Because if the truth table is short, then obviously classical algorithm just query the whole truth table. Anyway, so now truth table is much longer. F is 0, 1 to the n for some small n, and it's still Boolean function, it's 1 bit output. Okay? And now for our easy overall notation, we define 2 to n equal to big N, 2 to a small n equal to big N. And but now this function need to have promise. Okay, and we'll see this promising through all the algorithms with all the problems we talk about today. So this promise means that this function is actually not defined on every 0, 1 to the n bit string. Okay? So we say it's truth table. Yeah, and yeah, so this truth table is actually, I guess it's restricted. Okay, so not all possible n bit string is valid truth table for this thing, and so it has this promise such that it's either this truth table so this function is either a constant function. Okay, so constant function just means every output is either 0 or 1. Okay, and yeah, so if you think about the truth table as a big N bit string, it means that it's all 0 string or all 1 string. Okay, so truth table is all 0 string or all 1 string, and so that's one possibility, and another possibility is that it's balanced, and that means so once again we look up this truth table as a big string, and the balance means number 0 here equal to number 1 here. Okay? And so 0 and 1 can be distributed arbitrarily, but number 0 must equal to number 1. And I guess here we are basically assuming that the small n is an even number, so that you can have so number 0 is small n divided by 2, and number 1 is small n divided by 2. And we have an example here, so we see we have our example is a little weird. Okay, but anyway, our example is we have 5, 0 here and 5, 1 here. Okay, yeah. So as you see, this is a balanced input string. So we have 5 zeros and 5 ones. Okay, and so we spend a lot of time talking about this constant and balance, and that's because our problem is to decide whether your f is constant or balanced. Okay, so if you are given a constant input string, then your algorithm should say f is a constant input string, and if you are given a balanced input string, then your algorithm should say f is a balanced input string. Okay. Okay, and so we will give a quantum algorithm that solves this in one query. But before we do that, let's think about what's the classical Fourier complexity of this problem. Okay? Because we want to study a separation between classical and quantum. Classical is a bit easier. Okay, so classical Fourier complexity actually depends on details of how you define classical Fourier complexity. What I've been talking about is really loosely just we say classical algorithm and solve. What do we mean by solve? We need to think about how much error the classical algorithm make. Okay, so if you say the classical algorithm need to make no error, then it requires a lot of query. Okay, because basically you need to require more than half of the string to make sure it's either constant or balanced, right? Because say if okay, so this is so I should change the color to make this more useful. Okay. Yeah. So if you are really unlucky, then your algorithm might be like looking at the place of this string, and you look at half of them, and even though it's a balanced string, so it looks very different from this 00, 01, but maybe you just get really unlucky and look, you see all the zeros. Okay. So you might see n over 2 of the zeros, and oh yeah, oh I've been where right, 2 to the n. Okay, sorry, I've been talking about number wrong. Okay, so the number of possible zero is big N over 2. Okay, so not small n over 2. Okay, so I was talking this really wrong. Okay. Yeah, so number of slots here is big N. Okay, so small n don't need to be even number. I was confusing myself. Okay, so the number of 0 and the ones here are big N over 2 and big N over 2. Okay, and okay. So big N over 2 is 2 to the small n over 2. And yeah, so you might see big N over 2 number of 0 here, even though it's a balanced string. So you cannot make sure it's whether constant or balanced. And but if you get one more of them, then you are then you can be sure that you are either balanced or constant. Because constant you will see 0, or 1. And balance, if you have one more than big N over 2, then you must see two different symbols here. Okay, so yeah, if you want to do this in no error, then you need 2 to the small n over 2 plus 1 queries. Okay. Yeah, and this kind of query complexity is usually written as D of F, D for deterministic. So this is deterministic classical query complexity. Okay, and but if you allow some error, then we see that we don't need too many queries to to do this classical query algorithm with constant error probability. So say if you want error like 1 over 3, so you be correct. So usually we assume is 1 over 3 or error less than 1 over 3 or success probability or bigger than 2 over 3. Okay. And if you only want this, then you only need to sample constant number of position here, because you sample random position here, and so if it's constant, if f is constant, you are going to see 0, or 1. And if it's balanced, then the probability you see in 0 and 1 is 1/2. And so there are pretty small probability that you sample on balanced string that, and say you sample 10 of them, and you see 0 or 1 is like 2 to the probability is only like 2 to the 10 over 2, right? And yeah, so this can get to pretty small constant pretty quickly. Okay, and in randomized query complexity, we don't care about the error epsilon here too much, because you can amplify it with the majority rule. So you just keep doing the same algorithm faster. Yeah. So say if you have error 1/3 algorithm, then you can get error 1 over 10 algorithm pretty quickly by just repeat your algorithm a few times. Okay. Anyway, back to Deutch-Jorza problem. we see that we only want constant error, then it's pretty easy to do this classically with constant number of queries. So you just sample these things randomly, and you should see 0 and 1 with 1/2 probability. And probability you actually see all 0 string over 1 string is exponentially small in the number of query. Okay. Yeah. Okay. So we see that the classic algorithm don't actually require too many queries to do this if you allow random output. Okay. But what about quantum query? Okay. Quantum query is it's better than either of those in different ways. So it's better than this because it's you only need one query, so it's like an exponential improvement. And it's also better than it's randomized. It's constant versus 1, so 1 is still better than constant. And but also the quantum algorithm is exact. You will calculate the problem with perfect probability. Okay, so that's also a bit better than randomized. Okay. Anyway, so that's the quantum algorithm here. As we say, it's a generalization of Deutch-Jorza algorithm. So you see this is really similar to Deutch-Jorza algorithm. So only thing changed here is in Deutch-Jorza algorithm there is only one qubit in the input register. Now it has n qubits, so we put this headema to tensor to n here. So you put this headema tensor to n means you put a headema on every qubit here. And yeah, and it's the same phase keeping structure here. On the output register, you put a minus sign. Okay, and on input register, you put headema to n. Okay. And then this headema to n, we'll see a lot of it, and here we'll spend some time to teach you about how to calculate what headema to n do on the n qubit. Okay. And so let's first see what's headema to n on this 0 to n. So we have every qubit as a zero state as input, and we apply headema on all of them. Okay. And yeah, so this is really no intergoing happening here. So it's just every qubit become headema 0. So headema 0 to the n. And we know headema 0 is plus, so it's plus to n. Okay, so that's nice. We have a very clean form. But plus are not very nice for calculation actually, because like this UF we are defining it on computational basis. Remember once again, we have like UF of let me change the color back. Yeah. So we have so we do phase keyback, so we are going to get like UF of x and minus, is going to give us minus 1 to the f of x, x minus. And anyway, what we are going to see is we are going to get our result in terms of f of x, where x is a computational basis state. So this plus state is a little hard to use. We want to write it in computational basis. Okay, so let's write it down. So what's this thing in terms of computational basis? Each one of them is 1 over square root to 0 plus 1. So we have a lot of 1 over square root to the n of them. So it's 1 over square root to n. And then all other thing it has 0 plus 1, 0 plus 1, 0 plus 1, tensor n times. And so you do a distributed rule through all those strings, and then you find out that actually you have every possible string here, right? Because there are n register here, and each register you can pick either 0 to 1 to get this distributed rule. So actually you get all 2 to n possible string here. So you are summing over all possible string, because the all 0 string come from this, you pick a 0, 0, 0, 0 here, etc. And then you can pick a 0, 0, 0, 0, 1, and that's a 0, 0, 1 string. Okay, so headema to the n, we find out that it's actually this normalization factor and the summation of all possible x string. Yeah, that's pretty nice. We have a bit more condensed form here, so just sum over all possible x and this x computational basis state. Okay, and so that's back to analyzing the algorithm. So we found out that the first register is summing over all possible computational bases, and the second register, just like before, is minus. And let's go through this one again. Is 0 go to x become 1, and then 1 go to gamma become minus. Okay. So the input here is minus. Okay, and as we say, last time we do this nice fixed kickback technique, we see that the record register is minus, and what happens is you just, the record register stay minus, but you get a -1 to the f of x phase. Okay? And so if you plug this thing back to our side 1, then we see that, so by linearity, every x get -1 to the f of x, and you sum them together. So the state just out after you do the query becomes the sum x -1 to f of x, and then your x state. And once again, x is all possible computational bases of n qubit, and there is normalization factor 1 over square root to the n, and the second register state is minus state. Okay, and now let's look back our algorithm. Okay, so we know what's side 2, and then we do gamma to the n on the first qubit again. Okay, now there's a question. No, this is tricky. What's okay? So we want to apply gamma to the n on every possible computational basis state. And what is it? And this actually has a really nice close form that you should remember. That is, it is this thing. Okay. So gamma to the I guess. We'll see this longer. Okay, so this is the result as a spoiler. Gamma to n on nb string x is actually once again summation of all possible classical string z. Okay, and so z here is a dummy variable because it's summing over, just like x is dummy here. Okay, but we fix the x here, and so for every computational base state x, we see that the outcome is also summation of all computational basis state x, but with the phase either -1 or +1 depending on the inner product of x and z. Okay, x is an input string, nb string, and z is an nb string, and the inner product is like this. Okay. Yeah, so bitwise inner product. So if x1 times z1 plus x2 times z2 to xn times zn. And here we can write either plus or O plus, doesn't matter because it's a power of -1. So it's a naturally gamma 2. Okay. And yeah. But anyway, okay, so that's like a bit spoiler, but how do we get this? Okay. Let's analyze this by 1 bit in a 1 bit case as a start. So what's the gamma x? So if we have just n equal to 1. Okay, so gamma on 1 bit. So we know gamma 0 equal to 0 plus 1, 1 over square root 2. And gamma on 1 is 0 minus 1, 1 over square root 2. Okay. And so now we want to write this completely in one formula, and so we said 0 or 1 is our x, right? So x is either equal to 0 or 1. So we want a gamma on x. And now we see that it's always in summing over all possible z. So summing over all computational bases. So z is 1 bit, so it's either 0 or 1. Okay. So you are all summing over z and 1, 0, 1. Okay, so you are summing over all possible string z. So z is either 0, 1. But we have some phase here. Okay. So what are the possible phase? So phase is +1 here, +1 here, +1 here, and -1 here. Okay. So you get a -1 only when x equal to 1 and z equal to 1. And you can express that as x times z. Right? Because x or z are either 0 or 1. And so on those three positions you have, okay, so maybe I can draw here. So z, okay, maybe let's try this thing. Okay. So let's say it's z here and x here, and this is when z equal to 0, and this is when z equal to 1. and this is when x equal to 0 and x equal to 1, right? So you see that when either z or x equal to 0, then the phase here is plus sign, and only when they are both equal to 1, the phase is minus sign. So you can express that very succinctly with just minus 1 to the x times z here. Okay, and obviously you have a square root 2 here because you have a square root 2 here. Okay, so question on this one-bit derivation of Hedema on computational basis state. So really we already know this Hedema 0, Hedema 1 equal to this plus state and minus state, and but we know written in this. Well, in one bit is look like it's a really dumb way to do this because this looks more complicated than just writing in plus or minus. But as we see that this very algebraic form allows us to derive what happens when we have n bit. Okay? And yeah, when we have n bit, then every bit becomes this sum of z equal to 0 or 1, right? Okay? Because Hedema to the n and each bit really there's no entanglement between them, so you can just deal with them separately. Okay? So Hedema to the n on n different bit. And so each bit becomes a summation of 0 to 1. So you have the summation z1 to zn. They all equal to either 0 or 1, just like here. And each one of them give you 1 over square root 2 n of them. Then you get square root 2 to the n, 1 over square root 2 to the n. And then the tricky part is what is minus 1. Okay. So yeah, each one give you a minus 1 to the x times z factor. So you have a minus 1 to the x1 times z1, then times. Okay, so here we do a little calculation, right? Here we have the phase equal to. So the first term give you minus 1 to the x1 times z1, and the second term give you minus 1 to the x2 times z2. And the third term give you minus 1 to the x3 times z3, and minus 1 to the xn times zn, and then it's just a middle school math thing that the exponent, so you can combine everything by adding the exponent together, right? So this x1 times to the x1, sorry, minus 1 to the x1 times z1 times minus 1 times x2. Minus 1 to the x2 times z2 is just minus 1 to the x1 z1 plus the x2 z2, etc. So this is the basic multiplication become addition on exponent. Okay, and yeah, so this is our result. We see that there is a summing over all possible bit of z. So this is all in 0 1, right? In 0 1, it's ugly. Okay. Okay, yeah, so every one of them is in 0 1, etc. And yeah, and when you have this 1 over square root 2 n and minus 1 to this x1 times z1 plus x2 times z2 plus the xn times zn. And then that's exactly the result we say, because you have every bit is arbitrary 0 and 1, so you are summing over all possible bit string z. And the phase factor, as we say, is the inner product, so the bitwise inner product between this x string and the z string. So we think x as the n bit vector, and sorry, n dimensional bit vector is weird. So we think x as the n dimensional vector where each coordinate is either 0 or 1, and z is also n dimensional vector, each coordinate is 0 and 1, and this x dot z is like an inner product between those two 0, 1 vector. Okay? Yeah. So we have this form of h to the n x, h to the n on x, and yeah, it will be very useful in a lot of places, and you will see it in homework and in exam, etc. Okay, and anyway, finally we can back to our Deutch-Jorza algorithm. So we have psi 2 equal to this thing, and we basically don't care about the output register. And then we apply Hedema to the n on the first qubit, and we see what happens. Okay, so Hedema to the n on the thing that we said before is minus 1 to the f of xx, and this is normalization, and minus sign. Okay, and so minus sign is just like the not minus sign, the minus state. Okay, so minus state will stay minus state, and now let's prove for this thing and see what this is. So we have the summation x and minus 1 to f of x stay here, and then we have a sigma to n on x, and just we say it will be this thing. We'll get a whole bunch of another summation on z, and a whole bunch of factor minus 1 to the x dot z, and to the square root to n. Okay, and so how do we deal with all these things? So we have two summation, and usually the thing you do is you switch the ordering of summation. Okay, so we say, how about we sum x first, then we sum z. Okay, so sum z and sum x, and now let's group all the phase together. What kind of phase do we have here? So we have a minus 1 to a sum z, minus 1 to a sum z. And so that's minus 1 to the x dot z plus f of x. And normalized by 2 to n. Okay, and this really looks really complicated, but it has quite a bit of structure, and so the special thing is you can just look at what is this thing when z equal to O0. Okay, so what if we try to calculate when z equal to O0. Okay, so that's basically the amplitude of z equal to O0 string. Okay. And x dot z will be 0 because z is O0. Okay, okay. And then that's just become, okay, so this thing, the amplitude on z, when z equal to O0 is just sum over all possible x, minus 1 to f of x divided by 2 to n. Okay. And then we see that our problem is set up very nicely because when x is constant, then this summation is either 1 or minus 1. Because so you are either so f equals 0, then you are summing a whole bunch of 1. And so you are summing over 2 to n different 1, not different 1, 2 to n ones. Yeah, and then this whole factor become 1. And if ever x equal to minus 1, equal to plus 1, and then you are summing over a whole bunch of minus 1, and so this sum become minus 1. So either way, when your f of x is balanced, is a constant, then you see the probability is 1, because the amplitude on the z of your string is 1. So yeah. So when you because remember, like the next step we do is we are just going to measure the first register. So we are going to measure here, and maybe I'll change the color. Okay, we are going to measure here. So we really want to learn the amplitude here. Okay, so we're going to measure here, and so we just show that we actually totally know what's the measurement result when the input is constant. Because when input is constant, and when input is constant, then the amplitude on z being O0 has no square 1, and so it's always going to give you O0 string as output. And what if it's balanced? What if it's a balance? Then because it's balanced, so number of minus 1 here and the number of 1 here will cancel out. Because remember, f of x is 0 to 1, so this thing can give you, this thing is minus 1, so I don't know why I changed back, but I want to change back. So once again, remember this part is equal to, has two possibility equal to 1 if f of x equals 0, and is minus 1 if f of x equal to 1. And well, the number of minus 1 here will be same as number 1 here, just because how we define balanced. Okay. So we are summing all possible input, all possible x. So summing over all big N x. And we want to see what are the f of x. And just because how we defined, then we see that the number -1 turns on here and the number 1 turns on here is the same. And so they exactly cancel out, and so the amplitude for O0 is 0 when you have a balanced input. So when it's balanced input, we don't really know what are the distribution on Z, because they probably depend on f of x a lot. You have this weird, really complicated expression you need to solve. But once we know is that because we have this promise on being balanced, so it's really complicated how it actually distributed, but we know the O0 string is never going to get picked up because it will exactly cancel. Okay. Yeah. So there is this extra part of the algorithm we don't talk about. We actually kind of hide. Okay. So the quantum thing you do is this thing. Okay. So but there is an extra analysis that we need to do at the end here. Okay. So the end, we need to do a 1B decision, right? But we get an NB string output. So the extra thing we do here is if O0, if it's Z equal to 0, 0, 0, 0, then we say it's constant. And if Z is not equal to 0, 0, or 0, then we say it's balanced. Okay, so yeah, so there is a extra one piece of the classical analysis we do here. You get this NB output string, and you want to check whether it equal to O0 or not. And yeah, so that's the Deutch-Jorza algorithm. It perfectly distinguishing between the constant case and the balanced case of the input function with just one quantum query. Any question? Okay. And okay. If there is no question, I think we can keep going. We have still about 10 minutes to our break time. Okay. But there are a lot of elements that we'll keep seeing today. So this phase feedback and this head map to the N thing. Okay. We can use this to do a lot of different algorithms. And actually this whole circuit, as we will see, that we will use it to solve a different problem, I believe. Okay, yeah. And yeah, so we can use that circuit to solve a different problem. And that's the Berstein-Vazirani algorithm. Okay? And once again, it's a promise problem, and with longer input. Okay. So input still 0, 1 to a small NB string to 0, 1. And so once again, this is a big NB string. You can think about the big NB string. But but now we have a really weird structure that actually talk about this small f of x. So we said that this big NB string is determined by actually a small NB string. Okay, so there is this kind of secret small NB string that will actually determine a big NB string, because everything in this big NB string is just calculated by this formula here. So we say f of x just equal to s star x. Okay. And there is a secret string of the small NB. And I guess we should. Okay. So we think f as a big NB string and s as a small NB string. So maybe let's do an example of let's say example of So it's a bit confusing, although we don't really need to know detail, but I guess it's nice to write an example. So example, we have like n equal to 2 and let's say, oh, is this going to be too long? Okay, let's try. Let's see. N equal to 2 and let's say s equal to 2-bit string, right? So that equal to 1, 1. Okay. And so we can have, so we will have our truth table. That's actually 16 of them, right? So we have f of 0, 0 equal to inner product between 0, 0 and 1, 1, and so that's a 0, and f of, wait, actually how many of them? There are, I confused myself a little bit. So small equal to 2 and big N equal to 4. Oh, yeah, so it's actually a 4-bit string. Okay. Yeah, and yeah, so f of 0, 0 equal to 0, and f of 0, 1 equal to 0, 1 inner product with 1, 1, so it is 1, 1 here, and it's 1. And okay, and it's mod 2. And f of 1, 0 equal to is 1 and 1, so that's 1. Okay, and f of 1, 1 will equal to inner product between 1, 1 and 1, 1, and that's 2, but we mod 2, so that's 0. So that is. Okay, so you see that. Okay, so what I want to say here is that we have the 2-bit string, and then from the 2-bit string we calculate this 4-bit string 0, 1, 1, 0 as a truth table of f. Okay. So this is a very strong promise. This f, although it looks like a really long big and big input string, actually has some secret s that will just determine it here. Okay. And yeah. Okay, so that's f. And anyway, so now the problem is it's not a decision problem anymore. We want to the problem is find this s. So we want the longer output here. Okay. And so once again, we think about what we can do classically first. So classically, basically, every query will get 1 bit of information about something. Okay? And as we said, this s has a small n bit, and so really you need to do small n queries to find this bit string s. Just because classically you are only going to get a 0, 1 answer. Okay? Classically, each query you get a 0, 1 answer. So roughly speaking, you get 1 bit of information for each query. Okay? And so you need about n queries to do this thing. But we only give a rough example here. Yeah, so you need about n query to do this here. But we only give a rough argument here. Yeah, so you only give a rough argument as a lower bound here. And as for upper bound, you can really know that it's in n queries, because you can look query at these locations for f of for x. Okay, so you can query at this x1 tilde. That's this 1, 0, 0 string. And if you think about this inner product with s, this will give you the first bit of s. And similarly, if you pick x2 tilde equals to 0, 1, 0, dot, dot, dot string, and you think about what the x2 tilde inner product with s, it will give you the second bit of s, etc. So you query n of those strings, and you will learn whole s. And so here is like you see this one. So in the example here is these two things, right? So you see that you query the 1 0 and that's the first bit of S, and you query the 0 1 that's the second bit of S. This one. Okay. And yeah, so we can classically the query complexity is small n, although we give only a rough argument here. Now what's quantum query? Okay, so quantum query is really interesting. So quantum query can actually give n bit of information as in shown here, okay, because of the phase keepback. So we run the same algorithm as the Deutch-Jorza algorithm, and yeah, so like the quantum circuit part is the same, but we just do different classical pose. So this measurement result is like a Z or S here. So so it's a measurement result is Z here, and then we'll see that the measurement result is actually S here. Okay. And yeah, and so that's same analysis as we do in Deutch-Jorza algorithm. And okay, and yeah, so basically, well, it's the same circuit here, and so we have the same state here. So as before, as before, we say that we have this sum z sum x and 1 over 2 to n and minus 1 to the z dot x and plus f of x z. But now we have no, now we can, yeah, so we can start our analysis here. And but now we have a different promise on f of x. We know f of x is our secret s, the inner product with our input with this dummy variable x here. Okay. So f of x is also s dot x, and we can do weird linear algebra here. Okay. So we have the inner product with x and s inner product with x, and that's so you can do distributed rule, and that's z plus s inner product with x, and everything is mod 2, and so let's have this addition as mod 2. Okay, so it's a bitwise addition mod 2, so it means that you XOR every bit of them. Okay, and yeah, okay, so we have this weird thing as a phase. And yeah, and once again we already switch the order of summation. Okay, and yeah, so we have this sum z sum x 1 over 2 to the minus 1 to the z plus s, and the inner product with x. And once again, we are just going to measure computational basis. So we want to know this summation x term, what is this? Okay, and let's call this part a sub z, just because it make it a little easier. Okay. And yeah, and what we want to say is this a sub z part, which is summing x 1 over 2 to the minus 1 to the z plus s dot x. Well, we want to say that this thing is delta of zs, and that means that it is 1 when the z string equal to s string, and 0 otherwise. Okay, and so we get a bit of indirect proof here. Okay, and so let's write all this. So delta between z and s equal to 1 if z equal to s, is 0 if z not equal to s. Okay, and so we cheat a little bit, so we basically only prove this part. Okay, and so sorry, I write this wrong. So when z equal to s, not when z not equal to s. When z equal to s. So we can cheat a little bit. So when z equal to s, and then this is z plus s is bitwise XOR on every bit, but it's mod 2, so it's going to be the all 0 string. Okay, it's a 0 bit, so kind of like a 0 vector. Okay, yeah, and anyway, 0 vector inner product with any vector is going to be 0. So this minus 1 to a 0 is just a 0. Oh, sorry, minus 1 to a 0 is 1. Okay. So you're just summing over 1 over 2 to n and all possible x. There are 2 to n possible x and a equal to 1. And then the cheating part we do is that we know this thing is normalized. So this sum over all possible AZ square equal to 1, and when one of them is 1, then all other things should be 0. Okay. And you can check in homework that the cancellation actually work out directly. Okay, and I think it's time for a break. But yeah, but basically we have the Berstein-Vazirani algorithm here. So we see that if you run this thing and do a measurement here, and you will always get Z here. Oh, sorry, you will always get S here. Your secret string S. Okay, and let's have a 10-minute break, and we'll finish this class with a little more analyze on Berstein-Vazirani, and then we'll talk about Simon's problem. Okay.
好像还好，是不是？哦，那我跟他们讲一下。
Also, the meter is graded here, so you can pick out the meter here. Okay. And yeah, we will probably go over a few little meter explanation next Tuesday.
你有把那个就是期中考的成绩记录跟分那个，你有分题号的吗？也有分手记录。现在看的话，大家都看到。
算了，先不要画。
我回去看一下，再那个再处理一下。不该听吗？我大概生气了。你可以说一下那个序的，但是对吧？应该是会调分啦，就是也不太能保证它会调到什么程度，希望大家还是努力一点。
考40%，因为有22人，4个没考过，我觉得大概
大家。大家来这里，我想问你们每句文都不好写。每句文那个我这个作业差不多。第二题
就像期中考这样，3那就是在一直接着来。比如说，假设接着3个 H， 你看到找到 H 的这个公式，那你其实可能前两个现在全对变 或 H， 然后再变成 H， 就会变 H 等于 H 等于 H， 不会。反正就是如果就是一直，但是你这样矩阵的话就是这样，但是如果你可以不要用矩阵的样子，因为会更太难，对吧？那就是干嘛？就是用曲线，然后就是塞的时候会变就00，然后2个就会变成正的，然后再下一个，
因为那个时候就是看曲线，
对，
推不出来，可是感觉考试的时候爆开也没什么时间。
就如果忘记，然后还有时间的话，
对。
这个让他们拿回去，
什么东西？
考卷
看完了。对啊，看完就拿回去了。拿回去好好研究一下。好。对啊，虽然都没有题目，但是要那个。
题目也就没有不会放上去。
题目是这样，题目才不会放上去。就是讲解页上面有吗？有考古是没有，对，好像最好几年前有放吧，去年有放吗？
我不知道，没有。
对啊，我后来就觉得还是不要放，比较简单一点，单机都这样，也没有难度。不知道该不该放。
之后出题目，累到自己。
到时候那个下礼拜2讲解是会录影。
对啊，会录影。
对，都一样，跟上课。
对啊，应该是跟上课一样录影这样子。
好，谢谢。
今年是把这个发给他，算了，录音就放上去，录音应该是太好算。好吧，试试看。
老师 YouTube 是公开的，
对，我 YouTube 是公开的，所以 YouTube 应该会看到。试试看。
Hello. Okay. Let's back to our algorithm stuff. Okay. So we seen two algorithms today that has basically a quantum circuit, but just have different classical analysis. Okay. And so it's Berstein-Vazirani algorithm and Deutch-Jorza algorithm. It has that's really annoying. Hopefully we have enough power. Actually. Okay. Wait.
不懂哪里？应该是插在我的桌子上面，对一个小方形的。
Okay. Sorry about that. Hopefully we have enough power. And anyway, that's our quantum circuit. And so it really has the same structure. So we want to do phase keepback. Where do I? We want to do phase keepback. So we only use one quantum query, and we put the minus state at its output register. And we see that it can do phase keepback, and on the input register, we can do the superposition of all possible states. So we have the n bit of 0 as an input, then we see that we do this head map to n on 0, then it becomes superposition of all possible input state. And then we go through this UF, and you got this phase feedback, so we got this -1 to f of x. And we do head map to n again, and it becomes this really weird thing of now you have two dummy summations, so you sum over all possible x and so on, sum over all possible z. and you have the face minus 1 to the inner product with x and plus f of x. And then we see that with, okay, so it's really complicated here, but so basically these two quadrant we do two different promises on f of x to make this solvable. So we see that in the Deutch-Jorza algorithm, where are we? Yeah. In Deutch-Jorza algorithm, we restrict f to be either constant or balanced. Then we see that when it's balanced, then we can focus on this z being O0's bit string. Okay, so when z is O0, then we just have -1 to the f of x. And so we set up f of x to be balanced, then it's -1 to the f of x over all x will just be 0. Okay. And yeah, so that's the Deutch-Jorza algorithm. You can distinguish whether it's constant or balanced by seeing that when it's constant, you will always get the O0 string, and when it's balanced, you will never get the O0 string. And then we have a different promise in this Berstein-Vazirani algorithm or problem. And here, this truth table of x is actually defined by a much smaller string. We have a small bit s that determine the whole truth table of f of x. So f of x always equal to s inner product with x. And okay. Yeah. And then we claim that classically, so let's not say that one done. Yeah. And then we go through the circuit, and we see that now we have even nicer result, okay, because we have even more structure. So we see that we got this s dot z dot x plus f of x. Once again, we have this thing as the output phase here, but now our f of x just our s dot x, and we see that this means when you measure here, actually the measure outcome is always equal to s, because all other components will cancel out. Okay. And so we kind of use a weird trick to say all other components will cancel out, because we say the z equal to s component will have amplitude 1, and amplitude is normalized to be sum over sum equal to 1, and amplitude is normalized as a non-square sum to 1, and that means one of them is 1, or other thing is 0. And you can also check directly that there is cancellation in the homework. Okay, how much do I have? Anyway, any questions so far? So we proved that actually after you do the headmark here, this stage is just S here. So you measure and you will get S. And so this is quite interesting. This is very different from classical query. Classical query, you query once, you only get 1 bit outcome. But here you see, you query once, you can actually get n bit information out, because there are n bit input here, and you phase key back to make a n bit different string here. Okay, even though. Okay, so this thing's weird, but I guess it just works, because remember quantum query, we kind of starting at the start, we say we kind of say like the input stay as the same input here, right? Okay, thank you. Yeah, so the quantum query we started with saying input stay as the input, but we see that we can actually first keep back to do computation on the input, and kind of make it a totally different string, and get a lot of information out of it. Okay. So that's some weird quantum trick you can do with quantum query. And wait. This one. Okay, now we have power. Deutch-Jorza and the Berstein-Vazirani algorithm. And okay, so now let's get back to our discussion about separation between quantum and the classical algorithm. Okay? And yeah, so we see that Berstein-Vazirani algorithm is is a better, although it's a really thin circuit. But for this problem, we see we have a bigger separation than Deutch-Jorza algorithm. Because remember, we have a complaint about Deutch-Jorza algorithm. We're saying that if you consider you let classical to do randomized algorithm, then there is really only constant separation because you only need a constant query to see whether it's a balanced input or not. But in Simon's algorithm, then we see that we have actual more than constant separation, although it's kind of linear. So we have this 1 versus order n separation between quantum and the classical query. Okay, so yeah, so we have this kind of a polynomial separation. So 1 versus order 1 will depend on how you define. But anyway, this is a 1 versus order n separation. But we want to see whether we can get a bigger separation. So we want to get like a 2 to n separation. So we want the ratio between those to be 2 to n. Yeah, and obviously the answer is, well, not obviously, but we ask this because we know the answer is yes. Okay, and the answer is yes because there is this Simon's problem. Okay, and okay, so Simon's problem is like this. But now things are really different, so we are not on Boolean function anymore. So we have a function on 0, 1, so NP string, and the output is actually really whatever, but like a small, but let's say it's 0 to n. Okay. We'll see the whatever part pretty soon. Okay, and anyway, so first thing we need to do is we need to redefine our quantum query a little bit. Okay, and so we have been saying that quantum query look at this xy. Quantum query on xy, then you become xy o plus f of x. And this y o plus f of x is pretty well defined when yeah, so this o plus is really nice when we have yeah, it's pretty clear when we have y and f of x being 1 bit is just addition mod 2. And here y and f of x are NP string. Okay, and I think what we do is, okay, need to check. Let's say, okay, I think we don't want this. Let's say, although I think it doesn't matter. Okay, yeah, so we will need to define this to some kind of addition that's reversible. So let's say we have bitwise addition mod 2 here. Okay, so we just think y as NP string and f of x as NP string. Okay, to make things a little easier. I don't think it matters too much. So yeah, y NP string and f of x NP string, and this O plus is bitwise addition mod 2. Okay, just like before. So okay, so yeah, so that's like yeah, let's make a symbol consistent. So that's like this thing here. So the O plus S means you do bitwise addition on every bit. Okay, and so with this notation, you will have like something. So if you do this bitwise addition twice of the same thing, it will become the same thing back. And anyway, so that's bitwise addition. And let's go back to Simon's problem. So we say now f is now f has a much bigger output. So once again, but we still think the whole truth table of f as our input. and so we still have like a big N slot here. Okay, so this truth table still have a big N slot, but now only thing changing is that every block inside, instead of only 0, 1, you can have like 1, 2 big N. Okay, you have a 1, 2 big N number in each block. Okay, so that's the difference. And now, once again, we are promise problem. Okay, and it's a really weird promise. The promise saying that so you have this really long big string here, and okay, you have a really long big string here, and basically they are paired together. Okay, so some of them are paired together. Okay, I shouldn't do this. But there is a secret string S that pairs together the blocks inside. And when they are paired together, then f of x equals to fy. And so who are paired together depends on s, and that's when y equal to x, and this bitwise addition with s. And yeah, and this S is a secret, and the problem is finding it. And so I think I should get a better presentation of the example here. Okay. So that's the example here is, let's say n equal to 3. Okay, and our S is 1, 1, 0. And n equals 3, and so big N equal to 8. Okay, I'm a little regretting this now, it's too big, but I guess we have time. Okay, so small equals 3, big N equal to 8, and as we say, there are 8 blocks here, and they will be paired together by the secret S, and so there are going to be 4 pairs in them. And so what do we mean? So we have the block, let's see how we write. Okay. So we have f 0, 0, 0, f 0, 0, 1, f 0, 1, 0. Let's write down all possible input string. 0, 1, 1, f of 1, 0, 0, f of 1, 0, 1, f of 1, 1, 0, and f of 1, 1, 1. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and so what do we mean by this? So we say some of the function values need to equal to each other when y equal to x plus s. Okay, so those 3 bits are x over y here. Okay, and so who is paired with who? So s equal to 1, 1, 0. So f of 0, 0 should equal to f of 0, 0, 0 plus 1, 1, 0, and that's just 1, 1, 0. So this one should pair with this one. Okay, and their function value can be really anything, but we say it's a 0, 1 bit string, but we need like this being longer just because we want this being if only if. So when I pair together, they are the same thing, and there are 4 pairs, so we only need like 4 possible value here. And the value, whatever the value, we don't really care. So let's say this equal to 7, like 100, we don't care. 100. So let's say this equal to 7. Okay. And then what about next pair? So we have a 0, 0, 1, and we say so 0, 0, 1 plus and 0, 0, 1 plus 1, 1, 0 should be the same thing. So 0, 0, 1 should pair together with 1, 1, 1. Okay, and let's say this equal to whatever 5. And the next one, 0, 1, 0 and plus 1, 1, 0. So that's 1 and 1 plus 1 equals 0, and 0, 0 plus 0 equals 0. That's 1, 0, 0, 1, 0, 0. Okay, so those 2 pair together. Okay, and let's say this is equal to 4 because why not? And finally we are left with 0, 1, 1, and they will pair together with the level over 1, 0, 1. Okay, so let's check. So 1 plus 0 equal to 1, 1 plus 1 equal to 0, and 0 plus 1 equal to 1. Okay, and those two pair together. Okay, and maybe they equal to I don't know, 2. Yeah. Okay. Yeah, so that's like a possible input to Deutch-Jorza algorithm. Sorry, to Simon's algorithm. So you have those bigger input, and they are going to form, well, bigger N over 2 pairs. And how they exactly pair together is defined by the secret string S. And then once again, the question is you want to find the secret string S. Okay. And then now we have more example here. Okay, so an example of how you do this classic algorithm is basically you run collision finding. Okay. And so you just pick random x here and you ask what's f of x. And if you see two of them the same, then no, it's the same pair, and you can just calculate it. Okay, and for example, here we say maybe when we do this 0, 0, 1 and 1, 1, 1, we get the same thing. Okay, and then we have a different number here. So let's say we get like a 5 here, right? 5. Okay, let's try to because I do different random number here. I guess easier if I change this here. So let's say it's 6. Wait. 0, 1, yeah, let's say we have 6 here. Easier. So this is 6. This okay. Oh. Let's wait. Okay, it's big. Yeah, let's say we have 6 here, and okay, we're actually counting from 0. It's really annoying. Let's not have 0, 0, 0. Yeah. Okay, let's count from 0. It's really annoying. Let's say this is 0, and maybe this 0, 0, 0 thing is 5 here. Should just match with the example I have there. Oh, that's annoying. Yeah. So our example there says this is 5, and let's say this is 1, 0, 1. This thing is 0. It's slightly annoying. 0, etc. Anyway, what you do is you query random x here, and you want to find the collision. So maybe you see this 0, 0, 1 input string and this 1, 1, 1 input string, both give you 5. 0, 0, 1. Oh, both give you 6 as output. Let's say this is 6. This is 6. And this is 5, and I really don't like 0, 0, 0. Well, whatever. Okay. And this is 1. This is 0. Sorry, because it's 0. Let's say it's 1, 1, 1. So we don't have this weird. Let's pretend we don't have this counting issue. 7. Okay. Anyway, the thing we want to do here is we want to find collision, because we will find that we have the collision, then we know the x, y are related by this s, and we can find the s by just having x plus y, because let's do a small check here. So we say they are related to each other when y equal to x plus s. So x plus y will be x plus s, and that's twice of x plus s. But twice of x equals 0 because everything is mod 2, so that's just s. Okay? So yeah, we want to find collision. that's basically the, okay, so let's go to what's the classical query complexity of this thing. Okay. And you see that, so the output number label here is really arbitrary. So there's basically no information you can get except like where two things are equal or not. Okay? Because there is no structure, and sometimes you can even, it's a little confusing, but you can think about this quadrant like this can be even a larger space, so they are really far away, etc. But anyway, so you really learn nothing until you see a collision, and so the classical algorithm is just you pick a random thing and see when you get a collision. And but now things are a bit tricky. Okay. So you're going to sample random x, and you are going to get f of x. And the quadrant is when we'll when we'll see the collision, and you kind of think like, well, there are like n over 2 pairs, right? So there are n over 2 pairs, and every two of them has a probability 1 over n to be a pair. And so you can kind of think you need order n sample to see a collision. But actually that's not true, because you only need square root of big N. You only need square root to the queries to do this. And that's so the high level idea is that because the number of pair is a square of the number of sample you draw. So when you draw square root big N samples, you will get about order n pairs. And you are really checking the pairs. Okay. And this is a famous result is called the parallel paradox. That's saying that, so say we have a really small classroom right here right now. But that's saying that if you look through your classroom and ask whether two people has the same birthday, and with some pretty good probability, say probability 50%, and so the number of possible birthday is like 365. But actually, so you will think that you need about 300 people to get two people have the same birthday. But actually, you only need about 23 people to get this collision happen. And that's because of this square root happening here. Yeah. And so that's a Berstein paradox. And here is about the upper bound argument. And then there is also an argument saying that there is a tight lower bound. And anyway, we have a very rough argument for upper bound here, and really no argument for lower bound here, and those you can prove in homework. Okay, so with some probability analysis. That's the Berstein problem. So you see every collision happen with probability 1 over n. So collision probability is 1 over n. And but you really need like a square root to see collision. Okay, and that's classical. And anyway, finally we are going to see quantum algorithm. Okay, so how many quantum queries do we need to solve Simon's problem? And we cannot actually only need order small n query. Okay. So that will be exponential improvement. So classical is theta of, so 2 to the n over 2 is square root of big N. And then quantum is, I guess we don't need to write this. Okay. So classical is square root of big N. Square root of big N, and is 2 to the small n over 2. But quantumly, we only need the order small n. And now you see there is small exponential difference. Okay. And what's a quantum algorithm is still a bit similar to Deutch-Jorza. So we are still doing this hand to the n and the query and hand to the n. But we do different thing on the second register. So we kind of don't do phase kickback, but anyway, so we just input 0 to n here, and we measure measure it. Okay. Although, okay, so this is a bit funny. So here we put a measure here, but they actually do nothing to the first register because remember our analysis before we said like the reduced density matrix is unaffected by the reduced density matrix here. But anyway, we do measurement here to make things a little easier to analyze, as you will see, because what happens is those two states are entangled, and you measure here, and the upper thing here will become some easier to analyze pure state, I think. Okay. But anyway, let's just go through what these do. Okay. Okay, so we have a zero state input, and we go through headma to n, and as we know that we'll make this equal superposition of everything. And as we say, the second register we stay with 0. Okay. And then we apply our unitary, and so that should write your f of x into your second register. Okay. And okay. And so yeah, so there are all possible. There are 2 to n minus 1 all possible pairs, right? So there are big N over 2 possible pairs here. Okay. And okay. Okay. And then we do, okay, so that's the output state. Okay, then we do this weird 5-3 thing that make our analysis easier. Okay. That is yeah, so we do measurement here on the second register. Okay. So we measure this f of x. Okay. And as we said, we measure f of x in computational basis. And as we just said, f of x has all possible n over 2 values, right? So back to this example. So f of x is 5, 6, 4, 7. Is either one of those. Okay. So we are going to see one of the label. The real label number doesn't matter. Okay, but we are going to see one of them. And when that happens, I guess we didn't write out detail, but hopefully you can feel that. When that happens, so let's say we measure f of x to some number d, and then there are 2 corresponding x here that will give you the outcome as d, right? Like say, let's go back here. Say we measure d equal to 7, then x will equal x. The possible x corresponding x is 0, 1, 1, and 1, 0, 1. Okay. And so when you do this projection carefully, then you will see that when you select this f of x into a measure outcome d, then your first register is going to be projected back into this equal superposition of this 2p image of d. So you have some x and x plus s, where f of x equal to d. Okay, so this is a key step that kind of do nothing but make our analysis a lot easier. Okay. And yeah, so here we have the measurement operator we do. So we basically do, when you measure on D, you basically want to project the state on this identity tensor projector on D. And yeah, hopefully you can convince yourself that you do the projection on D, then the first register becomes this thing. Okay. And yeah, this should really not change our algorithm too much, because the actual outcome we want to get is the measurement result on the first register. But this makes analysis a lot easier because we focus on this component and it's just a pure state here. Okay, but anyway, so we do this thing, this kind of mental thing, and then we ask ourselves what happened. What is 5-4? Okay, so 5-4 is after here, then you do a headma to the n on the first register. So you do a headma n on this x and x o plus s, and hopefully still remember when you do headma n on something, is give you a sum of a dummy variable z, sum of another dummy variable, and 1 square root to the and the face of -1 to the whatever you have dot this new dummy variable z. So -1 inner product with x and z, and -1, and for this register, the input state is x or plus s. So that's -1 to the x or plus s inner product with z. Okay. So now we just deal with it algebraically. Yeah. And okay, so now we are back to very similar analysis as before. So we want to say that after this we'll measure z. So now the question is, what is this thing? Right? What is the distribution of this thing against z? Okay. And okay. So we have a -1 to a something plus -1 to a something. And our analysis saying that if you want non-zero amplitude, then this must equal to this, right? Because this is ±1 and this is ±1. So if they don't equal to each other, then they are going to cancel out. Okay. So they equal to each. So for z to have non-zero amplitude, those two things should equal to each other. And when those two things equal to each other, means the exponent must equal to each other. Well, mod2. We consider every calculation mod2. Okay. So that means x dot z equal to x plus s dot z. Okay. And then we do algebraic manipulation. So we multiply this out. So we see there are x dot z on both sides, and so we cancel x dot z on both sides. Then we just get s dot z equal to 0. Okay. So that's independent of x. Okay. So yeah. So as we said, whatever x we find out here doesn't matter. We are always going to get this relationship back. So we are going to get some z. So remember, z is the measurement outcome. Okay. Z is the measurement outcome. And okay, so z is not exactly s, so it's not as good as before. Z is not exactly s, but we see z has some relation with s. Z has its inner product with s equal to 0. Okay. mod2. Okay. And okay, then now we get a little hand wavy. Okay. And so we don't really prove here, so here is just claim here. Okay. We claim that z we got here, so how do I say? Z is kind of uniformly random all set of z's that satisfy this. Okay. Hopefully you think it's intuitive, because z really has no structure except that z dot s should equal to 0. Okay. And so z will get like a uniformly random. So I should say like a uniform random z in some sense. Uniform in some sense. Okay. So we'll get a uniformly random z such that s dot z equal to 0. Okay. And so actually, so our quantum circuit is here, but we'll run this many times. Okay. So each time we'll use one query. So we actually run this order n times. Okay. And we'll get many z as outcome. So we get z1, z2 to z order n. Let's say k equal to order n. Okay. And so we have a very informal argument saying that whenever you get one measure on z, then it's like you give one bit of information on s. And say example like if you get z equal to 10000, then you know like s1 equal to 0, and say you have z equal to 110000, then you know s1 plus s2 equal to 0, etc. And anyway, so we have this really loose claim saying that every z will give you 1 bit of information on S. And so you need about order n z to get the whole n bit string S. And then we have this into a little more detail is like saying that, so you can think about how you solve S when you get a whole bunch of z. Okay. So really this is a linear system equation. So you have S dot z1 equals 0, S dot z2 equals 0, so S dot zk equals 0. And so if you write all this as a system equation, linear system equation, and you will become, so you get this bit by bit. So you will have S dot z11 plus S dot z12 plus Sn dot z1 equals 0. I guess it's everything is all plus here, but yeah, we can treat everything as mod 2 as like a calculation in field of mod 2. Okay, so the first one will give you this linear equation, and the second one, so the z2 will give you another linear equation, and you just think about you get k linear equation, right? S1 to z k1 plus S2 dot zk2 plus sk dot zkn equals 0. So it's like you are solving linear system equations, so you can think about you have a big matrix Z and times this S vector equal to 0. Okay. And you can solve this S vector when your Z is like a 4 rank. Okay, so if you got enough linear independent Z, then you can solve the one Z vector that satisfy all those equations. Okay, so if you have enough linear independent get the rows, yeah. So if you have if you get how many do I need? Minus 1 linearly independent. We get minus 1 linear independent Zi can determine. Then we can determine S. Okay. And yeah. So here we have a bit of a probability theory that will tell us that you keep drawing those uniformly random Z, then you can use some probability theory to say that you draw order n of them, then you have failed. So like this O is maybe like 10. So maybe like you draw like 10 n of them, then you have very high probability to draw like every rank of this Z. Then you can get so you get is all of those n-1 linearly independent Z. Okay. And yeah, so we don't go into the detail of probability, but that's the idea. So I guess recap once again, our quantum algorithm look at this, and as we said, this measurement doesn't do anything but make the analysis a lot easier, so we don't need to deal with density matrix, etc. But anyway, so you do Hedema to n, so you input to your oracle with equal to general of everything, and then you Hedema transform, and you just measure, and the measurement outcome will be a Z that satisfies that the inner product with your secret string S equal to 0, and so you keep getting those random Z, and with about order n times, then you can solve this linear equation and reconstruct your secret string S. Okay, and now this is not deterministic anymore because you have some probability of drawing Z here. So if you get really lucky, you can keep drawing linearly dependent Z, and you will not get S. So this is not zero error algorithm, but if you draw enough time, then you have very high probability to determine your S. Okay, and yeah, finally we have the summarize of all the query algorithms so far. Okay, so we have seen 4 problem or 4 algorithms. So Deutch-Jorza algorithm, Deutch-Jorza algorithm, Berstein-Vazirani, and Simons. And Deutch-Jorza algorithm is a really small problem, and so you have a 1 bit input, and you just want, sorry, not really 1 bit input. 1 bit input to really small f. So your small f, so your truth table is a 2 bit string. And really we want to determine whether these 2 bits are equal to each other or not. And we see that the quantum query complexity is 1 and is exactly. And deterministic classical query complexity is 2, and randomized is obviously also 2. Well, I guess it's not so obvious, but you can prove that it's also 2. And then we have Deutch-Jorza algorithm, and it now has n bit input string to small n bit input string to this function f, and we say f is either balanced or constant, and we want to determine which. And the quantum query complexity is still 1 exactly, and this has no error. And deterministically, then we see that you have exponential separation. Now this is 2 to the n over 2 plus 1. But for randomized classical complexity, then we only need a constant number to get constant error probability. And then we have Berstein-Vazirani problem, where our f is determined by this short secret string s. So f of x equal to s dot x. And the question is find this secret string s. And we see that we can run basically the same quantum circuit as Deutch-Jorza algorithm. And the output will just be this s. And deterministic classical query complexity will now be n, because they are n bit. And randomized, you can also prove that it's order n. And finally, we have the biggest separation that's in Simon's algorithm. And that's when our problem has this weird collision, promise. So we say, so now the problem is really big, so it's n bit to n bit. And so the outcome can be a lot of different labels, although they don't really matter. Okay, so the outcome has really different labels. So it's like big N to big N. Yeah, so f is n bit to n bit, and okay, so I think it's like big N to big N. And anyway, and we say the outcome is paired into n over 2 pairs. Okay. And they are pairs by this secret string s. So the outcome are paired together if only if the input here has this weird relation. So x equal to x plus y. Okay. So if the x, y are related to this x equal to x plus y, then they have the same output label. So they are like a collision. And we just think that with the Simon's algorithm, and you can solve this with good probability in order n quantum queries. And but for classically, okay, so we didn't say deterministically, but deterministically, basically you need to one. So it's like the Deutch-Jorza algorithm problem. So if you want to deterministically find a collision, obviously you need to look through big N over 2 plus 1 of them, and you are guaranteed to find a collision. And but if you do randomized algorithm, then you have birthday attack, so you only need square root of big N to see a collision with high probability. Okay, and a bit of a review of the thing we introduced today. Okay, so the 2 things that you should really remember, first one is how you calculate kinema to the n on some classical on some computational state x. Okay. And we have derived this and show that kinema to n on x is 1 over square root 2 to n, and then sum over all possible string z. So now we sum over another dummy z, and minus 1 to the x inner product with z, and then z here. Okay. And yeah, and here this dot is a bitwise inner product. So it's you look at x as a nb vector, as an n-dimensional vector, z as an n-dimensional vector, and you do inner product on those on this vector of 0 and 1. Okay. And also we have seen this phase typic technique that's very useful when you have a Boolean function where output is just 0 and 1. So that's like when you put a minus state on the record register of your quantum query, then you see that the result is that you have this phase of -1 to the f of x on your whole state, and the minus state just stay as minus state, so you can kind of ignore it, and you just get -1 to the f of x to your input. Okay, I think we are 2 minutes early, but that's all I want to say today. So, any question? Otherwise, let's have review of the midterm once again on Tuesday. Okay, so see you on Tuesday.